So let's see the tutorial right now. So this is about 2 case studies. So in one case study, we are going to see how propensity works in marketing context, and then in another case study, as I discussed, we are going to see how propensity works for very similar in the credit industry or in the finance or banking industry. And then maybe let's also discuss if we have to follow the same approach for a probability of default modeling, credit risk modeling, what are the different things that we have to take care of, and what are the common things that are that could pretty much be used for both. So that's what we will discuss now. So let me, I'm using Google Colab, okay, so I am connected to the kernel right now, and as you could see, there is there are 2 libraries that I have installed, which is Colorama and scikit-plot. So these 2 libraries by default are not present in Google Colab, and that's why I have installed separately for this particular session. And these are used for generating some fancy plots and graphics that I will be doing. So that is the only purpose of this. Otherwise, the other models that I have, the libraries that I am importing here are primarily sklearn. I'm assuming all of these could be a bit familiar to you from your prior courses. Train, test, split, confusion matrix, this is for printing my tree, and then I am using sklearn metrics, right, so that gives you a bunch of default scores like accuracy, precision, F1 score, AUC, all those things. And then, I mean, what are we going to do without pandas in Python, right? So pandas, numpy, and then a bunch of other graphical tools. So I'm going to use all these libraries, and let's start with the credit propensity model. Maybe I can zoom a little bit, right? Yeah. So this is the data set, and let's have a look at the data set. So it is about a marketing a campaign. So you have to target which of the customers will be interested in buying the bike. Let's say this is a bike store, and when I say bike, generally in the West it means cycles, right? So in an Indian context, this is a cycle store, and we want to decide who would be interested in buying cycles from this store. And what data we got? We got data about customers and their marital status, single, married, their annual income. Yeah, in this case, you can think of it maybe in dollars, and then the family size, the children at home, not at home, and whether they are in a own house or not, and how many cars do they have, what's the age of the customer, and whether they bought a bike from the store or not. So these are particularly customers who visited the store before, and last column says during their visit did they buy that cycle, or was it just window shopping, they did not buy that cycle. So then let's have a look at how many customers are there. So there are about 18,484 customers here and 9 columns. So what is the modeling that we are going to do? So we are going to use these set of information, right? Particularly I'm talking about these 7 columns, the relationship status, income, children at home, other vehicles, house owner age. We are going to use only this and train a model that predicts whether that person ended up buying the bike or not, right? So what this model predicts is the probability of intention to buy, so which is nothing but the probability of interest towards that product, right? So in this particular case, I am building a propensity model that gives the probability that this person will end up buying that bike or choosing that bike. And if I could create this, what is the benefit? In the future, for any set of customers, I could just take these 7 information and input to this model, and the model predicts the probability of intention, and then I can sort them in descending order, and I can target the most interested folks if I want to do some campaign or anything of that sorts. So let's go ahead and do it. So this is the shape of the data set, and I'm just segregating the data set into X and Y, and in this particular line I'm writing a simple apply function where I'm changing S and M, you see here, into respectively 0 and 1, right. So if someone is married, they are going to be 1, if someone is single, they are going to be 0. And I'm assigning my target variable as bike buyer, which is binary, and it's already 0 or 1, so I need not worry about it. And let's look at the data now. Yeah, so if you see, marital status became 1s and 0s, so that's what it is. And what is the class balance? That's something that we have to check, right? And if we do a simple value counts, we can see that it's almost neatly balanced, so we need not worry about it this time. So it's almost close to 50-50. So 50%, 9,000 people ended up buying a bike and 9,000 people did not end up buying a bike, so almost balanced. So that's very good for us. And now with that, let's choose any classification algorithm to build a model. In this case, I have just opted for CART, classification regression trees, basically a decision tree. But yeah, you could very well use a logistic regression or any other algorithm, right? So before that, we have to split our train test. So I'm using the sklearn train test split, and yeah, it's 1/3, 2/3 proportion. So 1/3 test, 2/3 train, and I'm taking all. I'm not worrying much about hyperparameter tuning because this is just a demonstration, but I have just used all the parameters kind of available in decision tree classifier and set it as default values only, right. So you can just go to a sklearn page and look at the default values. I'm just putting default values, and I'm using a Gini purity here. So I'm not getting into details because that's not the objective. And then I'm fitting my decision tree here with my trained data. So that's exactly what I'm going to do. And yeah, so the decision tree classifier has trained in this case. But we have to generally do hyperparameter tuning, right? So that's where we figure out the best model. So in the interest of time, what I thought was, let me just take one of these hyperparameters and show you a demonstration of fine tuning it in our propensity use case, and then you can follow the same for other parameters as well, right? So in that case, the parameter that I have chosen is complexity parameter. So if you can see that it's being put as 0 in this particular case. So let me see which value of complexity parameter is the optimal or gives me the best results. So to do that, I am actually I'm just plotting my performance at different at particular different complexity values. And in this particular graph, you can see the x-axis is the complexity value starting from 0, 0.025, 0.05, 0.075 up till 0.0175, and y-axis is the impurity, right? And you can very well see the total impurity seems to increase, particularly when the values go beyond 0.025. The slope is pretty high. And let's do the same and let's look for accuracy in train and test for different values of complexity. So you can see in this particular graph, x-axis different values of complexity, y-axis the accuracy of train and test, blue color is train, orange is test. So if you see when complexity is 0, the train and test is like 85 and close to 76. So there's a huge difference between train and test. That's a clear indication of overfitting, right? So high variance, low bias, meaning it gives very good results in train but not so good results in test or real world. And when you go for different other values of alpha, I could see that that value gets more stable around closer to 0.025. So even with first 3 or 4 experiments, there is a huge gap, and then when it comes closer to 0.025, I think over here if we see, it's a bit stable and consistent around 70 accuracy. So you might question, why are you going ahead with a model that's 70 accuracy when you already have a model that's 85 accuracy, right? So I always prefer a 70% consistent model compared to a model that could give like a 85% in train and 75% in test. So consistency is the key when it comes to making decisions. And when I said accuracy, this is the accuracy of predicting whether someone will be interested in buying this bike or not, because that's our interest at the end of the day. So let's say I figure out now 0.0025 could be a good complexity parameter, and then I'll fit my tree that I'm going to use. And yeah, I'm just looking at the data type. So let's see. Okay, now what I'm going to do is I can visualize the tree and see. I have fit my tree with a best hyperparameter. Now let me just visualize this tree. So if I visualize this tree, it might take some time. Yeah, so here it is, right? So this is the tree that we see. We could see that the first root variable is number of cars owned, right? And of course the model doesn't know its number of cars owned couldn't be 1.5 or so. So we can interpret it in many ways we want. Okay, 2 less than 2 cars, less than 1 cars. So it says that number of cars less than 1.5, age less than 61.5, total children less than 3.5, age again less than 40. So you can see some sets of rules, and you can see some color shades, blue, light brown, dark brown or so. So what it means is that the blue is saying the domination of class 1, in this case buying a bike. The brown says domination of class 0, meaning not buying a bike, and darker it is, more the domination, right? So if I am interested in finding people who are going to buy my bike and then move towards that rule path, then these are the nodes, right? So these are the darkest leaves, and you can see that they are very dominated. So for example, this is the most dark, and you can see that out of 3,423 samples in this particular rule, 2,425 is actually ended up buying a bike. So it's very dominant, and that's why darker blue. But if you go to lighter blue, maybe you can see it's not that gap is not much there. Similarly, in the darkest brown, this is the case where someone didn't buy, and you can see it's so dominated, 499 out of 695 didn't buy. So based on my budget, if let's say my budget is I can target only 2,000 people to email out of 20,000, then which are those 2,000, right? So this tree visualization is giving me the rules, but it's exactly not giving me the customers. Hey, these are the customers, right? So you can visualize this tree when you want to understand rules, but when you want to go beyond and identify those customers, let's first predict, right? We are going to look at different metrics now. So we have the confusion matrix out here. That I'm not getting into details of confusion matrix because you're going to read about, you have already read, but you are also going to read about precision recall, F1 score, all those things in the next lecture as well on fraud. But generally this confusion matrix tells you how good is your model, right? And to decide how good is your model, there are various metrics, right? Accuracy, F1 score, precision, recall, and all those things. And you should do pretty well in almost all these metrics, right? So let's take recall. So in this model, the recall score is 0.6854. So basically 69%, right? And how did we get 69? This is kinda the confusion matrix. So 1512 people are actually buying, and the model is also saying buying, true positives. And then if you see 694 people, they actually bought, but the model sees them as a non-buyer, right? So false negatives are false. So if we divide 1512 divided by 1512 plus 694, it's actually true positives dividing by true positive plus false negatives. This value will be close to 69%, and that's exactly what we see here, right? And what is precision? Precision is 1512 divided by 1512 plus 1480. The model is predicting it as positive, but actually they are negative. So TP by TP plus FP. So that will be close to 51% in this case. And accuracy is everything, right? And then F1 score is harmonic mean of precision and recall. So these metrics tell you, okay, I think you're good. 69% you are able to find all the interested people, and let's say you seem pretty good, but still it's not giving you the metric that's required for ROI, right? So for that, there is a metric that we discussed in credit risk that is very useful. That's called KS, right? Comograph Monod. So KS we discussed, it's basically a gains table where we sort the customers from the most highest probability to buy this cycle to the lowest probability, and we are going to bin them and look at bad rates, right? So that we discussed that in detail. So let me first predict the probability and compute KS and print it. So we will see that the KS is 27.3, and what is output out of KS is this table, right? So this is the gains table. So we have sorted from the maximum most probability to the lowest ever probability, and it starts from 0.71 to 0.33, and in each of the bins we are seeing like some what to say, some event rates, right? So in this particular bin itself, you can see that there are about 412 events, meaning 412 people clicked, 198 people did not click, and so it is about 14%. What that means? 412 out of sum of all these events. So that is about 14%, right? And then you have various metrics, and highest KS is this decile, right? Sorry, this decile. Why? Because 53.91 minus 9.11, that's KS. So we discussed this, and that is close to about 27%. And if you look at one more metric that we discussed, capture rate, so that is this cumulative event rate, right? So now let's come to the budget. I want to target the top 20% of the people, top 30% of the people. If that's my use case, then I will know that if I have to target top 30%, maybe I can target the top 2 deciles, because the capture rate is 28.51. So if it is 43%, that means that when I just email or target the first 3 decile people, then I am able to get 43% of the interested folks, right? So this, and if I want to reach 90%, then I have to go at least till 9th decile. So how to evaluate a model now? So you will look at capture rate at 30 or 40% and see which gives you in the lowest deciles, right? Or vice versa. You will look at the capture rate at first 3 deciles and choose the model that has the highest capture rate. So that is one way you could interpret, and this is basically the marketing example. Now let's go to a bank example and quickly run the entire slides, entire codes, because we already discussed it, so I can be very fast. So let's see what is this particular data. It is about number of people being reached out for a credit product or finance product, I would say, fixed deposit, right? So the bank has called many people and approached them and asked, hey, are you interested in putting an FD? And then some people said yes, some people said no, right? So you have details about those, and now in the future you want to build a propensity model that expresses someone's interest towards putting an FD, right? And the kind of features you have is age, what job they are, relationship status, their education, and whether in the past they have defaulted on any loans with the bank, and their balance right now in the account. They have a housing loan right now or not, they have any personal loan. Contact means that what type of communication they are indulging or channel they are indulging with the bank, cellular or telephone, and then when was the last time they engaged with the bank, and the month, and last engagement how much time it lasted, and their how many campaigns they were a part of, number of days passed from the last contact, and then number of contacts, outcome of the previous contact, was it successful or they ignored the previous call, and whether they finally ended up taking a deposit or not, right? So it's very extensive information about the customer. So let's look at how the data looks like. So the last target variable is deposit, yes or no, and we need to binarize this column, right? So we will do that, and there are many categorical columns, as we could see. We have to encode that in proper way, right? So we'll do those things. So I'm using label encoder from scikit-learn, and I'm transforming the deposit column, which is yes or no. So that will now be transformed as zeros and ones. And for other columns categorical, I am doing get dummies, so that gives you the one hot encoding, right? So that is also being done. So let's just see what are the columns now. So you could see that in job you have a column for job admin, job blue collar, job entrepreneur, job services, job student. So basically it has done one hot encoding. So I'm making an assumption that you're familiar with all of these things, and let's just look at maybe a sample data of how it looks like, right? So this is how it looks like, and now I'm assigning x variables and y variables just like how I did before. So I'm going very fast here because it's the same code from the previous case study. I'm looking at class balance. So we are fortunate that it's close to 50%. And now I'm doing a decision tree, and similarly I'm doing a hyperparameter tuning for complexity parameter, and from here we see that the train and test is a little bit stable right from maybe here, right, between 0.00 and 0.02. Maybe it's not even 0.01, I would consider it as 0.00075, something like that. So yeah, that's exactly what I'm doing here. I'm using that complexity parameter and I'm training it. And you have all the confusion matrix and sorts. So I'm not going to tree interpretations. So let's go to the confusion matrix. So from the confusion matrix, we know that we are having very good performance, right? So 75%, 74% recall, 73% precision, and F1 score of again 73%. That's actually very good, but it's again not telling much about capture rate. So let's compute KS and let's look at capture rate as well. So when you look at capture rate is also very good, right? So in the top 5 deciles itself, I am able to capture 76% of the people who will be interested in putting an FD. So that's pretty good. And when we see the previous case study at 5 deciles, I didn't have a number that's close to 76. I'm doing much better here. So if I want to target 50% of the people who want to put FD, all that I have to do is target the top 3 deciles, right? So using capture rate, I can make these decisions much more easier. So top 3 decile, 4 decile, what percentage I target, and that is one thing I could do. And if I look at the KS, that is also better. Maybe the top KS is 49.5 at decile 5. So that is the overall KS of this particular model, right? And there is AUC, right? So I have plotted the AUC here. So what this also says, this particular model is doing pretty good for both the classes, class 0, class 1, and the best is actually class 1, right? And that's why the recall is also very high. So when in the world of finance and maybe in marketing also, this KS and capture rate comes in very handy, and what it tells is much different from that of an AUC or F1 score or precision recall. So that's why it's more business centric KS. It tells more about the outcome or or the business numbers. It's very closer to that, and that's why capture rate and KS becomes very useful in the world of credit risk and credit propensity. So hope you found it useful, and thank you.